Hello, welcome back to the review for Math 201 Statistics. We're going to begin with problem number 1 here. There's going to be several videos just to keep them shorter. So check them out. They're in the modules. Number 1 says, suppose X is a normal random variable with mean 100. Use the given normal distribution to answer the following. Do not use normal CDF or inverse norm. You won't be able to use the normal dist from Desmos because you don't know the standard deviation, okay? So this problem is really just about understanding the concepts of the normal curve. So one concept is that the center that makes it symmetric and cuts it in half is the mean. So we do know that's 100. And we also know that we learned this semester that the area under the curve is 100% or 1.0. And we always list area up here. So that tells us that the area of the probability, I should say, of being less than 83 is 0.04457. So A says, what is the probability of being bigger than 83? Well, that should just be 1 minus 0.04457. Which should be 0.95543. Then B says, find the probability that X is greater than 117. Okay, so 117 would be about right here. So what is the probability that it's bigger than 117? Well, we don't know the standard deviation to help us put it into the computer, but what we do know is 83 is 17 spaces from 100, and its area is 0.5 minus 0.04457. So that is going to be 0.45543. And also 117 is also 17 spaces, just bigger than 100. So that makes this area is symmetric, and then 0.45543. And then that makes this area over here bigger than 117, equal to the area that's less than 83, because they're the same number of spaces from 100. So 0.04457. Letter C says, find the probability that X is between 83 and 17. So that would be the white space here, and the white space here is between 83 and 17. So that would be 2 times 0.45543, which is equal to 0.91086. And then D says, find the probability that X is between 83 and 100. So that's just the space here from 83 to 100 is 0.45543. So just a conceptual understanding of what the curve tells us. Now let's look at example 2. It says, suppose Z is a standard normal random variable. Show all work, including a picture, and we're just going to be practicing getting some probabilities and reminding ourselves how the normal curve and the z-scores work here. So let's look at A. Find the probability that Z is between a negative 2.13 standard deviations and a negative 0.35 standard deviations. Okay, so we're just going to draw what this would look like on the curve. And so because we were given standard deviations, we're marking it down here. So but we are actually shading the space in between the two. So we want to know what is the probability of being in between the two right here. So we're going to go to Desmos. And the normal distribution is what we're going to use. And we are going to put in, since we're dealing with the normal distribution, the mean is 0 and the standard deviation is 1. And we're going to put a negative 2.13 up to a negative 0.35. And it looks like that probability is 0.3466 if I round appropriately. And then the second one says find the area to the left of Z. My curves today are not good. And so to the left of 2.34, which is a positive 2.34. So we're doing a lot of shading. And you can see on the answer key is the best way to look at this. But that means we don't have a limit on the left, but we do have a maximum of 2.34 on the right. And so, oops, there. I'm going back here. Okay, so I do want to see that. I'm going to turn this one off. I'm going to zoom fit so you can see the picture. This is what our picture should look like for letter B. Letter C says the area to the right of Z is 0.07. So this time they gave us the area. So we want to find the probability that Z is greater, because it's an area to the right, is greater than something. We don't know what it is. And that area is 0.07. So 0.07 out here. And so what we are going to have to enter into Desmos is 1 minus 0.07, because we have to enter left area and we want to know the Z that goes with that. I'm going to show you what that looks like when we type that into. It's right here in this line right here that's highlighted. It's the inverse CDF, because we're inversing our probability. So we're doing the inverse of the normal distribution. And we did 1 minus 0.07. And so our Z-score is positive, which would make sense because our picture is on the right. And so that Z is equal to 1.456. I'm sorry, 1.476. 1.476. And then part D says, find the Z such that the area to the left is 0.23. So that picture. So that picture is going to be, area is 0.23. And so it's this area right here. And we want to find the Z that goes with that. So that is the probability that Z is less than something is equal to 0.23. And remember that Desmos will only accept the left-hand area. So up here, we had to fake the left-hand area to get the correct Z, because the Z was going to be positive on the right. This time, we know the left-hand area is the 0.23. So we can put that straight up into Desmos. And I can copy my work that we did before, but this time we don't need the 1. We can just put 2, 3. And so that Z-score is a negative Z-score, and it is a negative 0.7388. let's look at example 3. Example 3, go back to our paper here. Example 3 says, find the following critical values. So we're looking for a critical value where alpha is 0.015. It's a left-tailed test. So because it's a test, it's a left-tailed test. And because it's strictly left-tailed, we don't have to divide by 2 on our alpha. And we want the negative z. So we want area over there to be 0.15. So I'm just going to draw a little picture here so you can see what that's going to look like. So we want the negative z over here where the area is 0.015. So similar to what we just did on the last problem. And B says, find the T alpha for a right-tailed test with alpha at 0.02 and the N is 7. And the reason we need the sample size is because for the T distribution, we have to use degrees of freedom, which is N minus 1, which is 6. So we are looking for the right-tailed area. And we'll do both of these in decimals here in just a minute, but I'm just drawing my picture. So we want the right-tailed area that's 0.02. And so we want T of degrees of freedom 6 and 0.02. And so we have to put in 1 minus 0.02 into Desmos. So let's go enter both of these into Desmos here. And the first one, we said we had to do 1 minus the 0.015 of a z. Oh, no, we don't have to do the 1 minus, I'm sorry, because it is on the left. We recognize that. And so it's going to be a negative z. So this is the negative z alpha is equal to a negative 2.17. And then for B, we have to do the 1 minus on this one. And so it's 1 minus 0.02. So we can just change that to 0.02 because it's a positive z. It's a positive t. So we have to also change to our t distribution on this one for part B. So t distribution, and we got to put in our degrees of freedom of 6 and the area. And so that t is 2.612. And I'm going to show you my paper. You can see. So the first one was a left-tailed z, and so that was a negative 2.17. The second one is a right-tailed t, and so with degrees of freedom 6, it's 2.612. Okay, question 4. Question 4 is another one that is more conceptual, just making sure that you're wrapping up the semester, getting the big concepts. So it says the distribution for a population of test scores is displayed below, and in the top left corner, each of the other 5 graphs labeled A through E represent possible sampling distributions of sample means of for 500 random samples drawn, one with a sample size of 1, one with 2, 4, 6, and 8. So here's our population distribution. It's definitely skewed left. And so the one that's the sample size of 1 is probably going to look very much like the population because it just has samples of size 1. So that's going to be letter D. Is going to be where we have a sample size of 1. And then still skewed, fairly skewed, is going to be sample size of 2. So that's going to be up here, letter C is definitely going to have, it's going to look a little less normal, but still a few, you know, several out here off to the left. And then letter A is going to be the sample size of 4. It's getting, you know, starting to look a little bit more like the normal curve, but still skewed. And then B is going to be the one with sample size of 6. It's not looking skewed at all anymore, looking normal. And then our last one, letter E, is our one that is the bigger sample size. And these are still fairly small sample sizes. So if you took like samples of size 30, then you're definitely going to start to look like a normal curve. So catch me back for another video in this review.